Okay, good afternoon, everyone. Welcome to the extra session of the problem solving session for NPTEL Data Science for Engineers. I'm your teaching assistant. My name is Pravalika, and I'm a PhD student and Prime Minister Research Fellow from the Indian Institute of Science. And in today's extra session is all about the recap right from the beginning, from the week 1 to week 8 of the problem solving sessions that we had. Gives just a recap. So I'll be saying everything that we have covered so far for the first 15-20 minutes. And then we will be looking at some of the topics that some of the students wanted me to cover again, right? And some of the topics that I haven't covered, but they wanted me to cover. Okay, so those all also will be discussed, right? And after that is done, most people have missed the first week. So in the first week where I was discussing about R code and how to use R code, how to run single lines and all of that, right? So some people wanted me to explain that as well again because they were not able to run the output properly. So taking all of that into considerations, I thought it is better to have one extra problem solving sessions. Okay, so this is basically like the recap and some extra topics. Okay, and then whatever questions you might have and a little bit about R, right? So these are all the things that we are going to cover for today. So that's the today's agenda, right? So let's start with a recap. In the first week, we have discussed a couple of problems from the previous assignments and the present assignments as well. And then I have also shared the R code, like how to use R in general, how to install it, and then how to use the R Studio. And then we have discussed about how what types of data types are there in R, right? And then we have also seen how we assign values to a variable in R. So there are two types how we assign them. So one is using equal to symbol, and the other one is using the arrow that is less than and then a dash symbol, right? And then we have seen how to find the class of a variable using the class function and also the type of function. And then we have seen some basic arithmetic operations between two numbers, addition, subtraction, multiplication, divisions, and modulo and exponent as well. Modulo means the one that returns a reminder. And then we have seen how to assign values to the variables, and then how to use print functions in different ways, and then how to use a separator in the print function, right? And then we have also seen how to install libraries and how to call libraries and how to use some functions which are in specific libraries, how to use help option in R studios, right? If any of you remember, can you just tell me how do we use a help function? Uh, so let us say I want to use a function called print. Okay. So if I don't know what print does, and if I want to know what does it do, then how do I do it? How do we use help in our studios to specifically know about a function? Okay, so what we do is we use a question mark and then followed by the function that we want to know about. Okay, so now if I want to know about the function print, what I would do is I would give a question mark and then I would write print. Okay, and then I run that line, and the R Studio is going to take me to the documentation of the function print. Right. So in such a ways, and then we have seen some inbuilt data sets that are available in our studios. We had called the library called data sets, and then we have taken a data set called air quality, and then we have taken the data from there, and then we had tried to plot between two variables, right? And then we have also plotted the functions like cos function, sine function, exponent functions, and then the d naught. Then we have seen how do we create a vector, right, in our studios. And then how do we have seen multiple ways of creating a vector, and then we have seen different ways of assigning values to a vector in a sequence, right? So if I want my vector to have 1 to 50 numbers, I can't always give like 1 comma 2 comma 3 and so far, right? And so what we have done is we have used the colon. So one colon 50. So it will take all the values starting from 1 to 50. And then we have seen how to take consecutive even numbers and then odd numbers as well. And then we have also seen how do we take consecutive numbers with a specific difference, right? So, and yeah, and then we have also seen how do we take a sequence starting from one random number, and we want like 20 numbers after this with a difference of 3 or 4. And we have also seen that. Then we have seen some basic operations on vector. So given a vector v, if I want to add three number to all the values in that vector, how do I do it? So we have seen for additions, fraction, multiplications, and divisions. And once that is done, then we have gone for two vector operations. So where we have taken two vectors, v1 and v2, and then we had tried to add all of that, subtract all of that, multiply all of both of them, and then make one the exponent of the other, and so on and so forth, right? And then we have done element wise comparisons, and then we have taken absolute difference between the two vectors, and then we have also seen element wise equality checks and inequality checks, and logical and logical or are also applied to the vectors, right? And then we have seen vector slicing and indexing. So that we have covered that in the first week. So that was like the basic art studio that we were looking at, right? So all of that has been uploaded on the Drive link. I hope everyone were able to access that, right? That was from the first week. And then coming to the second week, we have discussed briefly about the linear algebra. And in linear algebra, we have covered about vectors, matrices, and the basic operations between matrices, like the additions and subtractions and the multiplications. And then we have additionally looked at the determinant of a matrix as well, right? And then we have looked at rank. How do we find a rank of the matrix? And then we have looked at the null space. So null space is something that some of the students have asked me to repeat once again. So I'll be doing this after this whole part, okay, after the recap. So I'll go into that and I will explain null space and all the topics that are relevant to it, like eigenvalues, eigenvectors. And a student has asked about PCA as well. So that also will be discussed. Right. And then we have looked at rank nullity theorem, and rank nullity theorem is nothing but the rank of the matrix plus the dimension of the null space should be equal to the number of columns of that particular matrix, right? And then we have solved a couple of linear equations, right? And in linear equations, we might have like three different possibilities. So the set of equations that are given to us might have a unique solution. So that is only just one solution that the one finite number of solutions that the equations are going to have, like x equal to 1, y equal to 2, and things like that. And then we have consistent and inconsistent. Consistent meaning it has like infinite number of solutions. For example, if I say some value x into 0 is equal to 0. Okay, that's the equation that I'm giving. So no matter what value I give for x, the answer is always going to be 0 because it is being multiplied by 0, right? So X is going to have like infinite number of solutions. So that is an example of a consistent solution set, right? And then we have inconsistent solutions, and inconsistent solution is basically having no solutions. It's like saying 2 is equal to 0. So there is no solution to it, right? So that is inconsistent solution. But how do we know that a solution is unique or consistent or inconsistent? So a solution is called unique when the determinant is not equal to 0 and it's a full rank matrix. Full rank matrix is it means that the rank of the matrix is equal to the total number of columns or total number of rows of that matrix. Okay, rank is the total number of linearly independent rows or columns. right? And then for consistent and inconsistent, if the given matrix is not a full rank matrix, then we have to look at which type of a solution it is. Okay, so that is when the number of equations are equal to the number of variables. Okay, so all of these exist only when m is equal to n. So m being the total number of equations and n being the total number of variables, right? In case if the total number of equations are greater than the variables, then there exists no solution to it. And if the total number of equations are less than the number of variables, then it might have multiple solutions, right? And then we have also discussed about distance between 2 points. How do we take that? D is equal to root over x2 minus x1 whole square plus y2 minus y1 whole square, right? And then we have discussed about a unit vector. So unit vector is nothing but vector divided by its magnitude, right? And then we have seen orthogonal vectors. So orthogonal vectors, we call two vectors as orthogonal vectors when the angle between vector 1, v1, and angle between v1 and v2 is 90 degrees. So how do we know that it is 90 degrees? What we have to do is we have to take the two vectors and we have to do a cross product between both of vectors. Okay, v1 dot v2, and then we will, if at all we get is equal to 0, then that means the angle between both of them is equal to 0. Sorry, equal to 90 degrees. And then we call that as a orthogonal vector. Okay. So that is what we have covered in week 2. And then coming to week 3, week 3 is completely like interesting, and it was complicated to most extent. So we were discussing about random variables and how do we how they are categorized by probability measures, and how and the probability density functions, so the PDF and the PMF, and how parameters of the density functions is estimated. And also we have looked at the hypothesis testing. That is something, hypothesis testing is something that we use to make our decision based on the data and the hypothesis testing. The hypothesis that we are taking, we are going to finalize the data. Finalize the um, conclusion that we are coming to, right? So in that, we have discussed some important terms such as sample space, event, and probability measures. So sample space is set of all possible outcomes. So let us say if I am tossing two coins, okay? So the probability, what are the outcomes that I'm going to get? Both might be head, right? Head, head, and head, tail, and tail, head, and tail, tail. So all the possible outcomes. So all those four are my sample set for now, right? And events, and when it comes to events are a subset of the sample space. So if I'm saying, okay, now I'm having two coins and I'm tossing both of them, but I want my first coin to have only head as the outcome, then I'll be having only two outcomes, right? It is head head and head tail. So this head head and head tail are a subset of the entire sample space of four out of the four, right? So this second one is called as an event. And then probability measure, this is nothing but the probability that we represent. If I'm tossing a coin, I might get two outputs. One is head and one is tail. The probability of uh, the outcome being head is 50%, or that is equal to 1 by 2. And the probability of it being a tail is also 50%, which is 1 by 2. So we are representing the probability as a measure of some value, right? And that is something that we call as a probability measure. So in a given event, okay, if we or the sum of all the probabilities that of sum of all the probabilities of the outcome should be equal to 1. Okay, so and also the probability always lies in between 0 and 1. And if I'm saying there are two events, A and B, where both of them are independent events, then the probability of both of them occurring at the same time, that is the intersection of both the events A and B, is equal to the probability multiplication, the product between the probability of both the events. So P of A intersection B is equal to P of A into P of B, right? So we have looked at a couple of examples there, and then we have also discussed about conditional probability. So conditional probability is that we want to know the probability of one event given that we already know the outcome of the other. So P of A given B, right? And P, so in that it means that I want to know the probability of A given that I already know the probability of B, right? So that is the conditional probability that we have looked at. We have also looked at Bayes' formula, where P of A given B into P of B is equal to P of B given A into P of A, right? And then we have seen random variable. So in a random variable, we have two types. One is the discrete and the discrete random variable, and the other one is continuous random variable, right? So again, we have a probability distribution. So why do we need use probability distribution is because sometimes we get so many outcomes, it is not possible to track each and every outcome. So along with their probabilities, right? If I'm saying I'm going to take note of all the events that are going to happen right from today, maybe till next 10 years or something, then it will be impossible for me to take the event values and also the probability that at which it is occurring, right? So in such cases, we use a mathematic function to represent the outcome along with their probabilities, right? So we can't use the same probability distribution for both discrete random variable as well as continuous random variable. And hence for discrete random variable, we use a probability mass function, whereas for continuous random variable, we use a probability density function, right? Um, so probability distribution is used to understand the random variable. We should know probability distribution. It tells us the likelihood of each possible value or range of values at which it occurs. Right. So then we have discussed how PMF is represented and how the PDF is represented and how we are going to take it. And we have seen a couple of examples under both PMF and PDF as well. And then PMF and PDF are basically for just one way when we are only dealing with a single variable X or a single variable Y. But in case if we are having more than one outcome, okay, let us say if I'm having two outcomes, then we go for binomial mass function. So binomial mass function is for discrete random variables only. Okay, as the name suggests, bi means two and nomial means outcome. Okay, we have seen how we are going to find the function of it, the formula, and all of that has been discussed. We have looked at some of the questions related to that as well. And then how we have for discrete, we also have for continuous. So for continuous, it is Gaussian density function or the normal density function. Okay, so this is used to characterize the random errors. So f of x has a particular function here as well, and we have seen how the graph is and everything, right? So after that, we have also discussed about chi-square density function, and it's a result when v independent variables are with standard normal distributions are squared and summed up. We have changed the degrees of freedom in the R code for chi-square test. Sorry, chi-square density function. Sorry, I just keep getting test. Um, so we kept changing the degrees of freedom for this particular function. We have seen how the graph has been varied and all of that, right? That was quite a fun and cool experiment that we had done, right? And then we have seen the moments of PDF. So moments means certain quantitative measures related to the shape of the function's graph, right? The first moment is the expected value, and the second moment is the variance of it. I hope you all are at this moment are aware of the estimation, like the mean variance and covariance functions and all of that, right? It's really, really important for data science that you know all of these like in a first hand rate. Okay. And then we have looked at some sample statistics. So in this, again, we have like three majorly defined words. So the first one is population. So population is a set of all possible outcomes of random experiments characterized by the function f of x. right? And the sample set is a finite set of observations. So if we are doing a study, let us say in India, I can't take all the billions of people, right? I can't take all the billion people together to do a study. So rather, what I do is I take just some part of the entire population. So that set is called as my sample set. Okay. So only some finite set of observations I do. And then the third important one is inference. Inference is nothing but the conclusion that you come to after your study and anything like that, right? And then we have looked at the measures of central tendencies. So central tendencies are nothing but the mean, median, and mode. So in mean, again, we have three different types of means: geometric mean, arithmetic mean, and harmonic means. We have seen some questions across them and all of that. And then we have gone to hypothesis testing. So hypothesis testing, in hypothesis testing, the parameter that we usually look at is the mean, sometimes the variance, but usually in general we look at the mean, right? So the null hypothesis in a hypothesis testing that we assume is that if I'm thinking the mean is going to be mu naught and the system is going to calculate some mean, okay, based on the data that I have given to the system. So if both of them match, like what I am assuming the mean to be and what the system assumes, system calculates, system won't assume, it calculates. The system calculates the mean to me. If both of them are equal, then it is a null hypothesis. But in case if it is not true, and it's called an alternative hypothesis. Right. Then we have seen two types of tests, two-sided and one-sided tests. Right. Two-sided means when null hypothesis is nu naught is equal to 0, and alternative hypothesis is your mean is not equal to 0. It can be greater than 0. It also can be less than 0. Okay, that's a two-sided test. And one-sided test is like your null hypothesis is your mean is equal to 0, but your alternative hypothesis is your mean is greater than 0 or it is less than 0. So one of those two, but not both, right? So those are the two tests that we have looked at. And then let us say when there are two types of errors in this. Okay, they are called type 1 error and type 2 error. So type 1 error is that when you reject your null hypothesis, even though it is true, okay, then that is called as type 1 error and it is represented as alpha. And this alpha is called as a significance of a test. So when you are using your R studio, when you look for hypothesis, when you do this two-sided test or t-test or anything like that, you also get the significance of alpha there. So significance of the alpha is nothing but a type 1 error. Okay. And then we also look at type 2 error. So it is basically one of the two statements. When you accept null hypothesis, even when it is not true, or when you reject your alternative hypothesis, even though when it is true. Okay. So that is termed as beta, but 1 minus beta is called as the power of the test. Okay. Um, yeah, that was everything that we had covered in week 3. And then coming to week 4, we have so far we have looked at linear algebra and linear algebra and statistics. So in week 4, we have discussed about optimization. So we have looked at different kinds of optimization. So the best example for optimization that we have taken is if I want to go from place 1 to place 2, I might have different paths. So one might be optimized in terms of distance. One might be optimized in terms of time, right? I might reach faster if I choose one path. I might reach a bit slow, but it will be the shortest distance for me. And there might be any other path which is neither time optimized or distance optimized, right? I might have multiple solutions, but I have to pick the right optimal route for me based on the constraints that I'm having. So if I'm saying I have to go from point A to point B in 5 minutes, okay, then I will obviously choose the path which is having the least take time taken, right? But if I'm saying I don't have time constraint, but let's say my bike may not have that much of petrol in it. Okay. So I definitely need to take the shortest path possible, right? So based on a given constraint, I am picking the best optimized route for me, right? So that was the best example that we can take for optimization, right? And then we have looked at univariate optimization problems. So in that we have three things. One is objective function and the decision variable, and then the constraint. So objective function means the f of x. It is usually some equation that we have. And then the decision variable, it is a variable with which the objective function is given. So it is either x or y, things like that. And the constraint. So we have the constraint like x should be greater than 0 or less than 0, right? Or x is equal to 0, or x belongs to a real numbers and all of that, right? We have looked at global maxima, global minima, local maxima, local minima as well. And then we have seen the necessary condition for x to be a minimizer, that is f dash of x is equal to 0, right? And the sufficient condition for it is f double dash of x is greater than 0. Okay, that is way, these two conditions are way too important for you to find a minimizer at all points, right? And then we have dealt so many problems in this particular thing, right? We covered up quite a few. And then we have looked at multivariate optimization conditions. So instead of having just one variable, we'll have multiple variables like x1, x2, x3, so far and so forth, right? And the necessary condition for that is the gradient of f is equal to 0. So that is the part we take the partial differentiation of the of the objective function f with respect to each and every variable that we have, like x1 and x2 and x3. And we write all of that in form of a vector, right? And that should be equal to 0, right? That is the necessary condition. And the sufficient condition is that the Hessian of f of x should be a positive definite. That means the matrix with positive eigenvalues. Okay, so yeah, I hope you all know how to calculate eigenvalues and eigenvectors and all of that, right? So from that you find if the if the values are local maxima or local minima. Right, and then we have discussed a couple of problems around it, and then we have come for unconstrained optimization problem. So so far we had a condition like x should be this, like y should be this, x should be in between this and this, right? And then when we came to a problem, unconstrained optimization problem, we don't have any conditions there. We are automatically searching for the minima or the maximum. Right. For that, we use the gradient descent. So it is applicable to find the minima of the given functions applied in the Bragg propagation algorithms to find the parameters as well. Right. We have seen how to do that. How do we where do we start the iterations and how do we go towards the search and everything. I hope you all remember that clearly. Right? And then in week 5, we have discussed about the constraint optimization. So we have seen unconstrained optimization, and in constraint optimization, I am giving a specific value. Like I have to go from point A to point B, but in between, I have to stop in point C to deliver something, right? So that is a constraint that I am having. So based on this constraint, now give me the path that I want to go. Okay. So again, in that constraint also, we have two types of constraints. The one is the equality constraint, the other one is inequality constraint. So equality constraint is x1 plus some x2 blah 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 is equal to some point 12 or something like that. And inequality constraint is that it is greater than 12 or less than 12 and so on. Right? So for equality constraint, we have looked at Lagrange multiplier, where it's an optimization problem plus a constraint problem. So Lagrange multiplier helps finding the optimal solution of a objective function while satisfying one or more conditions, right? So for that, the equation is the gradient of the objective function is equal to minus lambda times the gradient of the constraint that we have, right? So the lambda being the Lagrange multiplier. Okay, and we have covered quite a lot of questions around it, right? And then we have gone to inequality constraint optimizations, where we have more than one constraint. And then we have it like not equal to something, but it is like greater than or equal to something, or less than or equal to something, right? And then we have also looked at multivariate inequality constraints. So in this, we have multiple variables, not just one variable, but we have multiple variables. And then we have looked at the process of how to do it. First, how do we write the Lagrangian equation for it, and the first order KKT conditions also, right? Um, yeah, and then we have looked at a bunch of questions related to it and whatnot. And then we have seen the introduction to data science, like how uh, how one should think about general data science problems, and how you convert a problem that you know, which is not well defined, into something that is manageable using some techniques that you learn, right? Uh, and yeah, we have seen the different types of learning, like supervised learning and unsupervised learning. And then we have looked at the regression. How do we deal with regression problems, right? So regression is when the output is in terms of numbers, but not classification. And then we have seen ordinary square and testing the goodness of fit. And also we have again covered about hypothesis testing specific to this one, right? And then we have calculated the means and the covariance and the deviations from the means and the coefficients as well, right? We have looked at the different types of tests, R square test, adjusted R square test, and all of that, right? Mm, yeah. And in week 7, we have gone through the basics of neural networks, right? And how neural networks work. And mm, sorry, this is something. And then we have seen the difference between parameters and hyperparameters, what are the differences between both of them, and how one is involved with the model and the other one is not, not a trainable parameter, right? And then we have looked at cross-validation and the classifications. We also looked at logistic regression, even though the name says it's regression, but it's a classification problem, right? And then we have looked at performance metrics. In performance metrics, we have seen two types: confusion matrix and ROC curve. So in confusion matrix, when we were dealing with it, we were only just looking at 2 by 2 matrix kind, right? Positive, negative, positive, negative. But then in the previous class, when we had to deal with more than two classes, then we had a doubt, right? So I also discussed about that in general at the end. Okay, I hope that should also be clear. Mm, Second. Right. And in the previous class, we have looked at the classification. We have majorly looked at two things. One is K nearest neighbor, and the other one is K mean clustering. So we have seen how do we implement the algorithm and how we have done it in our studios. And we have also briefly discussed about the different types of learning, that is supervised learning, unsupervised learning, and reinforcement learning. Supervised learning means you are giving the label to the training data in the training data. So you are training the model while you already know the ground truth. And in unsupervised learning, you don't have the ground truth, and you are just telling the model to learn by itself, right? And in reinforcement learning, you are going to reward the system whenever it is right? For example, the self-driving cars. And then we have looked at the k-mean clustering, and we have seen the algorithms, how do we implement the algorithms, and we have also seen how do we do it in the R studios, right? And then how do we choose the value of k in k-mean clustering. So we have also discussed all of that, and we have covered some uh, assignment questions as well, and some other external questions also, right? So, and we have also seen how do we calculate the WCSS, that is within cluster sum of square difference, right? And then how do you choose the value of k is nothing but you have to plot the graph between WCSS and the number of clusters, and wherever you find the elbow point, that is going to be your k value, right? So that is the overall recap of all the 8 weeks that we have done in the problem solving sessions. So we'll just take a 5 minute break, okay, and then we'll continue with some of the topics that some of the students have asked to cover. Okay, so majorly I'll be covering about null space, how to find eigenvalues, how to find eigenvectors, and also PCA, right? So these are some few things that I'll cover, and also the confusion matrix for more than two variables, right? More than 2 cross 2 matrix. Okay, so we'll be covering all of that. Let's just take a 5 minutes break, and we'll be back by 3:40. Okay. Yeah, let's continue. I will just share my other screen. Right. Mm, yeah. So we have covered eigen values earlier, right? So given a matrix A, which will become- so given a matrix A that I have, okay, let us say it has some eigenvalues which are represented as lambda. And now I want to know the lambda values, right? So what I have to do is I have to take the determinant of A minus lambda times I, where I is the identity matrix of same shape of A, and this determinant should be equal to 0. Okay. So if I'm taking an example, okay, minus 5, 2, and minus 7 and 4. Okay. So I would say 5, 2, minus 7, 4, minus lambda times I. I is the identity matrix. So in an identity matrix, the diagonal numbers are equal to 1 and the rest are 0. Right? Then 1, 0, 0, 1. So this should be equal to 0. Right? So minus 5 minus lambda, 2 minus 7, 4 minus lambda. The determinant should be equal to 0. Right? Minus 5 minus lambda into 4 minus lambda minus. So I hope you all remember how to calculate the determinant, right? So you basically take the cross product of this value and this value minus the cross product between this value and this value. So 2 into minus 7. That should be equal to 0, right? So here if I'm doing it's minus 20 and then plus 5 lambda minus 4 lambda plus lambda square, minus into minus is plus, 14 is equal to 0. Right? It's lambda square plus lambda and minus 6 is equal to 0. Right? If I have to write it, I can write it like lambda square plus 3 lambda minus 2 lambda minus 6 is equal to 0. Right? So if I take lambda common here, it is lambda plus 3 minus 2 common here, lambda plus 3 equal to 0. So lambda plus 3 into lambda minus 2 is equal to 0. Right? So lambda values are minus 3 comma 2. So these are my eigenvalues. Are eigenvalues clear? Okay, cool. Right. So then comes the eigenvectors. So eigenvectors are nothing but, let us say we have a vector x, okay, and then our matrix is A, then it should solve, this equation should be true for it, right? So let us write it for what A is. Minus, minus 5, 2, minus 7, and 4. And for x, I can write it as x1 and x2, right? Which is equal to lambda times x1 and x2. Okay. So I can uh, rewrite this one as, if I bring this the other side, lambda x1, sorry, x minus a times a into x is equal to 0. Right? So here 0 is not just a singular value of 0, it is basically a 0 vector. or a matrix based on whatever we have here, right? I can take x common, maybe this side, and x common, that is equal to 0, right? So we already have two eigenvalues, right? We can take one of them. Let us say I want to take lambda equal to 2 for now. Okay. So I simply can't write lambda like this. Instead, I have to write it lambda times some identity matrix. Okay. So it's 2 into 1001 minus minus 5, 2, minus 7, and 4. Okay. All of this into x1, x2. This should be equal to 0, 0. Right? Let's solve for this now. It's 2002 and then minus minus 5, 2, minus 7, 4. X1, x2 is equal to 0, 0. And then minus of minus is plus, and 5 plus 2 is 7. And then 0 minus 2 is minus 2. 0 minus of minus 7 is plus 7. And 2 minus 4 is minus 2. Right? And then we have x1 and x2, and that is equal to 0 and 0. Right? So this is all fine, but now I want to write this equation as an augmented matrix. Okay, we have augmented matrix where I write this as 7 minus 2, 7 minus 2, and then I draw a line here, and then I write whatever is here. It is 0 and 0, right? So this is called as an augmented matrix. Okay, so why I do this is that I want to reduce the form of this. So what I am performing is something called as reduced row echelon form. Reduced row echelon form, where I want to make this one equal to 0. Okay, by using some row operations, by doing some row operations, I want to make this one equal to 0. Right? So looking at this, it is very clear that this value and this value are both the same. So this is my row 1 and this is my row 2. I can say I can convert R2 as R2 minus R1. If I do this, what will be my value of this? Sorry, of the whole thing. Okay. R1 will remain the same, right? But R2 is R2 minus R1 now. 7 minus 7, 0. Minus 2, minus of minus 2 is 0. And then 0 minus 0 is 0. Right? Now, that is okay. Now, this one became 0 for me. That is all fine. Now, what I want to do is I want to make this equal to 1. Right? So, for R1, I divide the whole thing by 7. Okay? So, it is 7 by 7 is 1. And then minus 2 by 7, and anything divided with 0 divided by anything is 0, and then 0, 0, 0. Right? So this is my row reduced row echelon form. Okay. So now my solution is going to be in such a way that okay, the solution is going to be minus 2 by 7 times of s divided by s. Okay, this s can be anything. Okay, it's basically like x, or you can just write x. Okay, so for any value of x, s, this is going to be the vectors. Okay. Uh, okay. But we don't want it to be in a fraction. So instead, what I'm going to do is I'm going to multiply this vector by 7 so that we obtain a simpler description. Okay. So it's minus 2 and then 7. Right. So this s can be any value. Okay, so this gives a basic eigenvector for lambda is equal to 2. Okay, where these values can be anything. Okay, is it clear? How I got 1? Is it this one? Basically, I'm dividing this whole thing by 7. This whole thing, basically. This whole thing by 7, so that this becomes 1, and this becomes minus 2 by 7, and this becomes 0 by 7. So this would be the output. I took this one. Okay. So you can do it for lambda equal to minus 3, I think the other one, right? Yeah. So you can do it for lambda equal to minus 3. Okay, I'll give you 5 minutes time, and then you can tell me what answers you have got. Like, what are the eigenvectors that you have got for that? Okay, I'll give you some time. Why did you take minus 2 by 7 comma 1 and not 1 comma 2 by 7? So it's just a matter of convenience. So both are actually valid. So both the vectors represent the same directions in the null space. So either if you take that or this, it's both going to be same. Okay, that's a really good question that you have asked. Okay. So are you guys done? Are you done for lambda equal to minus 3? Okay, so we are running short on time. So we'll just continue for now. Okay. Oh, really good, Lavanya. 1 is right. Okay, so that is how we find the eigenvectors. Okay, so shall we take a function that has like more than two values? Okay, so let's say 5 minus 10 minus 5, 2, 14, 2, minus 4, minus 8, and 6. So anyone want to try this? Okay. So in this, I'll tell you beforehand self. So once you get the augmented form, sorry, once you find for this one, since it's a 3 cross 3 matrix, we have at least the maximum we can have are like three eigenvector values here. So once we find the augmented form, mm, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So you make this and this equal to 0 and this one equal to 0. Okay. And then you try to make this one equal to 1 and then try to make this one equal to 1. So mostly once you do this, it's enough. You don't have to necessarily do this. So making these three 0 is important. Okay. You perform all kind of row operations and everything, and you try to make these equal to 0. And then eventually you will get your answers. Okay. Uh, you can try this later. Okay. But if time permits, I'll explain it at the end. Okay. Okay. So try later. So now let's discuss about null space. I just wrote a couple of conditions here. Even I usually forget the conditions or the mandatory necessary conditions kind. So yeah, before we discuss about null space, there is something that you all should know about subspace. Okay, if I am representing the subspace as S, okay, then then I messed up. Okay, so let us say this subspace S has a zero vector. Okay, so this zero vector is denoted by O, and that belongs to the subspace. Okay, in case if I have two vectors that both belongs to this subspace, then it is also said that any operation between the summation of both the vectors will also result in that particular subspace values only. Okay. And the other condition is that if C belongs is a real number and V1 is from a subspace, then CV1 belongs to the subspace only. Okay, so these are some of the three important conditions that you need to follow in a subspace. Okay, so now null space means, so in linear algebra, the null space of a matrix is the set of all vectors that when multiplied to a matrix, it will result in a zero vector or a zero matrix. So if I'm saying I have a matrix A and then I multiply it with something with a matrix called X, okay, then it should result in a zero matrix for me. Okay, so this should happen. Okay, so this can also be written as, and null space is written as n of A. Okay, so null space of A. So it can be written as if X belongs to R of n. So if n is n cross n, then X is going to be n cross 1, and this is going to be m cross 1, right? So if X belongs to some real values like n, right? And uh, what is it? rows such that A of X is equal to O is 0. Sorry. Okay, so this is how it should work. Okay, so it is a fundamental concept in understanding the properties of linear transformations. Okay. Okay. So this is R of R in n-dimensional space, and AX, this is a matrix and vector product, right? So the geometric interpretation that you can take from this is that the null space can be visualized geometrically as a subspace of R of n, right? So in what since X belongs to this, what we can directly say that according to these three properties is that uh, null space n of A is a subset of R of n. Okay, so R of n is a subspace here. Hope I made some sense, but even I'm not sure if I made any sense to you. Okay, so let's look at an example. Okay, so that it will be easier for all of us. So this is my matrix A. Okay, and X should be what? X1 and X2, right? So according to the condition that we have for null space, what we have to write is like AX is equal to 0, right? So 1, 2, 3, 4 times X1, X2 should be equal to 0, 0. Can you find X1 and X2 values for any value? So it is X1 plus 2X2 and then 3X1 plus 4X2 is equal to 0 and 0, right? So X1 plus 2X2 is equal to 0 is one equation, and 3X1 plus 4X2 is equal to 0 is another equation. Can you guys find X1 and X2 values and let me know that? Can you guys solve this X1 and X2 values and let me know what are the values for it? They are 0. I don't think so. Let's see. This is too much. And this, I can write X1 is equal to minus 2X2. I can put it in this. It's minus 2X2 is 4X2. Oh, yeah. Hmm. Okay. Then we shall go with row echelon form. That only should work. Yeah, they are also. Mm, no, I'm getting it as X1 and X2. Give me a second. Let's write it in the augmented matrix form, right? 1, 2, 0, 3, 4, and 0. And then let's perform row operations to it. R2 is such a way that R2 minus 3 times R1, right? So 1, 2, 0. R2 is 3, 3 minus 3 is 0. And then we have 4, 4 minus 3 2s is 6. So this is minus 2 and then this is 0, right? So now what do we do? Minus 50 and x2 is equal to minus 2, right? From this. Just give me 1 second. X2 is okay. Got it. Okay. Sorry for the really long pause. Okay. So if you look at the bottom one, right? Now you will understand that x1 is 0. So now you leave that aside. And then you have this x2 part, right? Just a second. So you have x2 is equal to minus 2, right? So x2 is equal to minus 2. And if we are taking this one, let us take just one equation. Let's say I take the first equation, right? I can say it like x1 plus 2x2 is equal to 0. So x1 is equal to minus 2 times of x2, right? So let us say I, instead of solving all of this, okay, instead of solving all of this, I want to write it in an equation form. I mean, a vector form with some variable. So x1 is minus 2 times x2 and x2 is just x2. Okay, so this x2 can be some variable. It can be x or t or s or something, right? So I can write this as minus 2 s and this is s, right? So if I take that s as common, so this is going to be my null space. Okay, I'm not sure if it is going to be the same if we are using the other equation. Oh, yeah, we don't take this equation. Instead, we take after we have written it in augmented matrix and then after we have performed the row echelon form, we are having only this, right? So we take this part. So 1 into x1 plus 2 into x2, and that is equal to 0. And from this, x1 is x1 into 0, so that is 0, plus x2 into minus 2. So that is x2, sorry, x2 is equal to minus 2. Okay. So overall, that is how we find the null space. Okay. Is it clear? So here S is a scalar value. It can be anything. So this means any vector of this form will satisfy Ax is equal to 0. Okay. And thus this is called as the null space of a matrix. Okay. Um, Now we quickly go into principal component analysis. Um, so I don't think it's that much necessary right now, but since one of you has already asked, I'm just writing. Okay, so this is a topic that is used for dimensionality reduction and also in some methods of machine learning. Okay, so this is basically used to simplify a large data set into a smaller set while maintaining some significant patterns and trends, right? Let us say I'm having some data from 1,000 people over a couple of years, right? I don't have the storage capability to have all the data with me, right? So instead, what I do is I try to apply PCA to it so that I will reduce the amount of data that I have while I'm also conserving the patterns or the trends that are happening in that data. Okay. So PCA, we can do this analysis in 5 steps. Okay, we'll go through all the steps, providing a logical explanations of what PCA is doing and simplifying the mathematical concepts also. So the main concepts that we usually look into this is standardization, covariance, eigenvalues, and vectors. So that's something which we have seen. No? Okay. So again, I will not be focusing on how to compute them. So you have to do it on your own. Okay. So the 5 steps include first we have to standardize the data that we have, and then we compute the covariance matrix to find the correlation between variables. Okay. And then we compute the eigenvalues and eigenvectors for that covariance matrix to identify the principal components. And then we create a feature vector to decide which principal component to keep and which one to let go. Okay. And then we recast the data along the principal component axis as well. Okay. Um, okay. So just write it here. The first one is standardization. So the aim of this step is to standardize the range of the continuous initial variables so that each one of them will contribute significantly or equally to the analysis. Okay, so if I'm taking images, okay, what I have to do, as soon as I get images as my data, before I proceed with any kind of machine learning or deep learning or anything like that, what I have to do is I have to standardize everything. So I take each and every pixel value, okay, I remove the mean of it and then divide it by 255. Okay, you all know the values range from 0 to 255, right, in pixels. So that is something that I do. So every pixel value will be taken and I remove the mean value of that entire image or the entire data set and then divide it by the standard deviation. Okay, so the reason why it is crucial to perform standardization prior to PCA is that the latter is quite sensitive regarding the variance of the initial variable. So let us say I'm taking two kinds of images. One is like having reduced brightness, or else we are taking just the same image, okay, and one has like high reduced brightness or contrast, but both are basically the same images that I'm dealing. Okay. Just because the pixel values are different from each other, I might get different values out. So instead, what I do is I have to standardize it. Okay, so that if there are any large differences between the range of initial variables, those variables with larger ranges will dominate over those with smaller ranges. Okay, so this will lead to some biased results. So hence we transform the data to comparable scales. Okay, so for that, what we do is we take the value minus the mean of it and then divide it by the standard deviation. Let us say this is image one, okay, and this is image two. I take one pixel box. Okay, maybe it is having some x dash minus. I remove the mean of it and then divide it by standard deviation. So I do that for each and every box. Okay. So this is for images that I'm talking about. But if you are having just a normal data, for normal data also you do the same. Okay. So this is how we mathematically do it. So we subtract the mean and divide by the standard deviation for each value of each variable. So once the standardization is done, all the variables will be transformed to the same scale. Okay. Yeah, so that is the first step. The second step is covariance matrix computation. So, do you guys remember the covariance formula or is it long forgotten somewhere in the woods? Do I need to study null space for final exam? Null space has been covered as one of the topics in the recording lectures, right? So it's good if you have understanding of it. And yeah, exam point of view, it's good that you have some perspective and some knowledge around it. But at least in later parts also you will need it. Okay, I can't comment anything regarding the exam. So if it is covered in the original recordings, then yes, you definitely need it. Okay. Now coming to the question, you should. I'll get back to you, Godwin, once this PCA is done. So okay. In this computation. The second step is covariance matrix computation. So the aim of this step is to understand how the variables of the input data set are varying from the mean with respect to each other. Or else it's like basically knowing what relationship is there in between two variables. Okay, because sometimes variables are highly correlated in such a way that they contain so much of information, and sometimes we don't need we like the variables doesn't have any correlation, right? For example, what we can say, it's like giving water to a plant. Okay, so if I water it at regular intervals, let us say once every day or once every 2 or 3 days, based on the plant that we are watering. So if I water, the plant will thrive, right? So so the relation between me watering it and the plant growing is related to each other. So if I remove this watering information and I'll just say the plant is growing, but for what reason? I'm removing the reason of it, right? So then I may not know. Yeah. So for some instances, there is high relation between why something is happening with some other data. Sorry, with some other data. So these data are something that we should not remove away. Okay, in order to reduce the dimensionality, we will remove some data out. But this example which I have given, so putting water to it, it's not specifically a data set kind. It's just a real world example. Okay. So in order for this relation to find this relation, we usually have this covariance matrix. So we compute it, right? So let us say I'm having three variables x, y, and z. Then my covariance matrix is covariance of x comma x, covariance of x comma y, covariance of x comma z, and then covariance of what should this be? Y comma x, right? And covariance of y comma y, and covariance of y comma z, covariance of z comma x, covariance of z comma y and covariance of z comma z, right? So these are the covariance with itself. So covariance of a variable with itself is called as a variance. We'll just write the variance of it instead of a covariance. Okay. So this whole diagonal is going to be the variance. And we actually have the variance of each initial variable. And since the covariance is commutative, so this value, covariance of x comma y, is equal to covariance of y comma x. And the same goes for this and this as well, and this as well, right? So covariance is commutative in nature. We have already seen that. And so, yeah. So the entries of the covariant matrix are symmetric with respect to the diagonal, which means the upper and the lower portion are equal. Okay. And not only that, the sign of a covariance also matters. So if the covariance is positive, then two variables either increase or decrease together. So they are directly proportional, or we call it correlated. Okay. Uh, so it's like if one of the variable is increasing, the other is also going to increase. So they're like directly proportional. So if the covariance is negative, then they are inversely correlated, which means if one variable is increasing, the other is going to decrease, and vice versa. Okay. So now you have to understand that the covariance matrix is not more than a table that summarizes the correlation, but it's between all the possible pairs of variables. Okay. So after this is done, we calculate the eigenvalues and eigenvectors of the covariance matrix. So this is usually done to identify the principal components. Okay, eigenvectors and eigenvalues are the linear algebra concepts that we need to compute from the covariance matrix. Okay, so as I said, this is in order to identify the principal components of the given data. What you first need to know about eigenvectors and eigenvalues is that they always come in pairs. So we have like two eigenvalues or two eigenvectors, and for a three dimensionality data set, there'll be like three variables, and hence we'll have like three eigenvectors and three corresponding eigenvalues, right? So yeah, it is. So these two are the main important ones behind the principal components, and they're actually the directions of the axis where there is more covariance. That is, sorry, more variance. That is most information that we have. So this most information that we have is something that we call as the principal components. Okay, and eigenvalues are simply the coefficients attached to the eigenvectors, which gives the amount of variance that is carried in each principal component. Okay, so it's quite complicated, I understand, but try to catch it up. Okay, so what we do is we rank our eigenvectors in order of their eigenvalues. That is from a descending order, from the highest to the lowest. And then you get the principal components in order of significance. Okay, let us say I have V1 and V2. It can be some values A, B, and this is C and D. Okay, it can be anything. And lambda 1, I have it like maybe let's say 1.5 or something, and lambda 2, let us say it's 0.5. Okay. So here the important thing is lambda 1 is greater than lambda 2. So when we rank it in the descending order, we are saying it's lambda 1 is greater than lambda 2, which means that the eigenvector that corresponds to the first principal component, that is PC1, is V1. Okay. And the vector that corresponds to the second principal component, PC2 is V2. So this is of higher significance than compared to this. Okay. So after having the principal components to compute, what we have to do is we compute the percentage of the variance or the information accounted for each component. Okay. So that is done by for this one, the percentage is lambda1 by lambda1 plus lambda2 into 100. Okay. And for this one, it is lambda2 by lambda1 plus lambda2 into 100. Okay. So then we'll get how much percentage each component is of value. Okay. And the highest percentage will will automatically be the one with the higher information. Okay. Oh yeah, week 8. Okay, I'll upload it as soon as the session ends. Okay, I forgot it last week. Thanks for pointing it out. Okay, so that is the step 3. Okay, so once again, we'll have a quick recap. The first thing what we have to do is we have to standardize the data that we are having. So we are going to do it by we take each value and then remove the mean value from it and then divide it by the standard deviation of the entire data set. So that is going to do the standardization for the whole data. So once that is done, we take multiple variables that we have and then we try to find the covariance between each variable, right? So with X and Y and Z and X and Z. So we find all the covariance matrix and then we come to a conclusion which one is how each one is correlated with others, like based on this sign. And since we already have the covariance matrix, we find the eigenvalues and the eigenvectors on the covariance matrix that we have just obtained. Okay, so those are all the 3 steps. Yeah, and the step 4 comes to the step 4 is to create a feature vector. So in this step, what we do is to choose whether to keep all the components or to discard those of lesser significance. So here we have seen V1 and V2, and V1 is having higher significance than V2. Right? Let us say I'm having more than 2. Let us say I'm having maybe P1, PC2, and so on up till PC50. Okay. Now I have arranged all of them in descending order. Okay. And at the end, the last 10 were giving less than 0.1% significance or something. Now, I have to come to a decision that how many should I remove out of this 50? So the main goal of PCA is dimensionality reduction, right? From 50, I have to reduce my dimensionality to some extent, right? Now, how many principal components should I remove, which are of lesser significance? Means the after arranging it in descending order, the lower ones that we have to choose. Okay. So the ones with low eigenvalues, right? So once we remove those with whatever we want to retain, so with that we form a matrix of vectors, and that is something that we call as a feature vector. Okay, so the feature vector is simply a matrix that has columns, the vectors of the components that we decide to keep. We don't want to remove them, we decide to keep them. So this makes it first step towards some dimensionality reduction, because if we choose to keep only some number of eigen vectors out of n values. So if I'm saying I have n vectors in total, okay, and I want to keep only p of them, keeping, okay, I'm only retaining these. Okay, the final data set will only have p dimensionals and not n dimensions. Okay, is that clear? So it's basically like if I'm saying A, B, C, D, this is my n cross n. Now I will change it to, I'll just keep only 2 of them, maybe A and C. So This is 2 cross 2, and now it is becoming 2 cross 1, right? So I'm reducing my dimensionality from this to this. So this is going to be my feature vector, the one which I want to retain. Okay. So it is up to you to choose whether to keep all the components or discard the ones of lesser significance, depending on what you're looking for. So basically, that comes with your learning. Okay, as much as you have some hands-on experience, you will decide on how many to keep and how many to remove. Okay, right? And then let's go to step 5. The step 5 is to recast the data along the principal components axis. Recast the data. Okay. So in all the previous steps that we have seen, apart from the first step, apart from the standardization, you do not make any changes on the data. You just select the principal component and form the feature vectors. But the input data set always remains in terms of the original axis. That is, whatever axis we have taken initially, with the initial variables, with all the variables together, right? So in this step, what this is the final one where we aim to use the feature vector formed using the eigenvectors of the covariant matrix to reorient the data from the original axis to the ones represented by the principal components. Okay, so this can be done by multiplying the transpose. I'll just write it here. Multiply the transpose of the original. Let us say the original is A, okay, original data set by the transpose of the feature vector. Let us say it is F, okay. So our final data set is going to be the feature vector transpose into the original data set transpose, okay. So this is entirely about PCA, okay. Uh, can we just take 5 minutes break? Can we just take 5 minutes break? I just want to fill my water and come. I'm out of water. Okay, I'll just come back in a minute. Okay. Okay. So I'm back. Okay, there are a couple of questions. How to consider PCF of 50 parts with three features each: time, distance, and load columns with each 400 rows of data. So that's pretty much the same that we have discussed so far, right? So we are have, according to your question, we have 50 parts, okay, and then like we have taken X, Y, Z here, right? So here you're saying we have time, distance, and load, right? So yeah, it's pretty much the same. First, what you do is you take all the data and you standardize the entire data, right? And then you calculate the covariance matrix. So the covariance matrix is again going to be 3 cross 3. And then you find the eigenvalues and the eigenvectors for this covariance matrix. And then you uh, have to create this vector feature, feature vector, where you have to keep some and remove some. So out of those three, you might keep one or two or three based on the significance it is giving. Okay, and then you recast the entire data. So that is pretty much it. Okay. Week 8 notes as yes. I'm so sorry for the delay. I'll do it. The minute the session ends, I will immediately do it. Okay. What kind of questions can be formed in PCA for final exam? Okay. See, whatever has been covered in the lecture slides, not in this one, the recorded lecture slides, that will be it. Okay. This one is specifically, I have gone in depth and explained step by step because a student has asked. Okay. So these are the things that I am discussing, even though there is some mentions of PCA in the lecture, it was not in depth. So hence I have gone in depth and I was explaining each and every step together. Right. So whatever is there in the lecture slides, if you are perfect with it, that's all you need. Okay, I can't comment on what kind of questions will be asked and things like that. Could you explain how to take the null space of any given adjacent matrix? Uh, it's pretty much the same. In place of A, you are going to keep your adjacent matrix and you do it. So get AX is equal to 0 and you can find your answer. PPT I will upload. Space is this. Um, Implemented question, we should be taking minus 2 by 7 plus 1. And why is that? Why do we take plus 1? I thought it was minus 2 by 7 comma 1 before when I was reading. Um, the augmented question, please reframe it and write it again. We don't take minus 2 by 7 plus 1. We write 1 in form of other. It's like x1 is equal to 3 times x2. Okay, and then we write it like 3 by 1. So if I'm saying x1 is equal to 3 times x2, then what x I can write it as 3x2, x1 in x1 place, and x2 place I'll write it as x2 only. So this x2 I will represent as some random scalar value. It can be this or this. And then I write it like this. So this is what happens in general. We don't write plus 1 minus 1. Okay. Okay. So yeah, that is that. And the other one, just give me 1 second. Okay, the other one that I wanted to cover was confusion matrix for more than two classes, that is a multi-class classification, right? So let's say I have three classes. class A, B, and C. Okay. So one side is my predicted values, and the other side are my ground truth. Let's just say the original ones. Right. So predicted ABC and ground truth ABC. Let us say I have 10 of each classes. Okay, I have 10 different images. Okay, let us say I have images and it can be a cat or dog or any other or mouse. Okay. Okay. So I'll say the model has predicted some values right now. Okay. Okay. Let us say the model has predicted if A is if 10 images are A, it has predicted that 7 are A and 2 are B and 1 is C. Okay. And then when it came to B, it has predicted 8 are B and 1 is A and 1 is C. And when it came to C, then it has predicted 9 as C, correct? And then 1 as B and none as A. Okay. So now what I can do is I can make multiple confusion matrix from this. Okay. Saying I want to know about A. Okay. So given that uh, the image is A, it's positive. Okay, positive or is A, and the prediction is negative, that is B or C. And then the ground truth is this side. So it is positive A and negative is B or C, right? So I can write this one in form of this for each and every class. Okay. So in this, from this table, I can write for a given value of A and the prediction is also A. That is this, right? The ground truth is also A and the prediction is also A, and I can write it here, right? And here, if I take the original positive value is this, but negative predictions are this 2 and 1. So 2 plus 1 is 3. I can write it off here. Okay. And uh, the other things that the model has predicted as A is this only one, right? Which is this one belongs to a different class B, yet my model has predicted that it is A. So that is the prediction is positive for A, but the ground truth is negative. It is negative for A. So here I'll write 1. Okay. My prediction is either B or C. Okay. My prediction is either B or C. And my ground truth is also negative for A. So these values come. Is this one clear? Uh, or did I just confuse you guys even more? Is this one clear? Okay. I can either write it as this way. Okay. So this is my predict axis, and this is my ground truth, ABC and ABC, right? For a given value of A, my prediction is also A, means that it is true positive, right? For a given class A, if it is either predicting as B or C, it is a false negative. Okay. And this one is true positive here for B and B, and this one is true positive here for C and C. The other all are false negatives only. Okay. That is the overall confusion matrix that you can write. Okay. But in case if you want it for a class specific, then you can write it this way. Okay. A bit confusing, not clear. Yes. Okay. Just give me 1 second. Um, is this one clear? This part? Yeah. Okay. Right. Okay. So now here I'm saying this is prediction and this is ground truth. Ground truth is A. And this one is B or C. I'm clubbing these two together. Okay. A and this is B or C. Okay. So how many values do I have where the ground truth is A and the prediction is also A? That is 7, right? I'm writing as 7. How many values are there when my ground truth is A, but it is predicting something else? My ground, see, I'm looking at this whole part right now. Okay. My ground truth is A, but the predictions are B and C. It is 2 plus 1, right? 2 from class B and 1 from class C. Okay, it's 2 plus 1. I'll write it over here. Okay. So this whole part is done. Now I'm looking at this side. Okay. I'm saying my prediction is A, but the ground truth is B and C. My prediction is A. The ground truth is B and C. Prediction is A, but my ground truth is B and C. I will look at it. Look at this one. So it's 1 plus 0. So that is 1. Okay. And this one is my predictions are B and C and my ground truths are B and C. That is these 4 values. So 8 plus 1 is 9 and this one is 10 and 10 plus 9 is 19. And this is. So this is specific to only one class, class A only. So like that, I can do class specific like class B and then class C. Also, I can write different confusion matrix. Okay. So this was also asked last week. So I just wanted to cover it here. How to find R square value for a given table if the question is the mod. We have already discussed about R square and adjusted R square. We have discussed the formulas and everything. Please put all these values in the formulas and you will find it. Okay. Uh, any more questions? Okay. Please don't ask me any questions regarding the exams. Okay. Will data set based questions come in exam? So maybe you will be given like 10 or 12 numbers in a table and you'll be asked to calculate covariance, mean, median, and all of those things. Okay, so something that is doable with pen and paper. Okay, it won't be too complicated. Okay, nothing will be too complicated. Uh, it will be fine. You will be able to answer. This question asks how to do. We have discussed the R square formula, right? R square formula is not that big, and we have solved some examples using that formula as well, right? If you want, I'll go there. I'm not remembering. We have taken a data like this x and y, and then we have found the mean, the deviation, the covariance, and R square. We have put all the values there, and we have finally got the answer. Okay. So this is how you do it. You remember the formulas. You have to do it by yourself. How to probably use assignment one. Actually, there is a confusion regarding whether to use given y or from per problem. Which is like the confusion regarding whether to use given y or from intercept obtained. Sure. Just give me a second. I'll look at what question is. Like, I'll just need to look at the entire question. Can you just tell me from which week that was? Anyone? It's from which week assignment? I think it's week 5 or something. Six. Okay, just give me a second. Is it the coupon rate and the bid price one? Bonds.txt. That one? Is it the bonds.txt one? That Session 9. Okay. Right. The model build from is y is equal to this. Okay. It is of this form. See. Okay. I didn't get your question, guys, because see, you have to calculate y cap. So here y cap is nothing but y is equal to 0.2x plus 60, right? You keep all the x values here one after the other, and you will get your y cap, right? So you have all your y cap values, and y is already given. And for r square, it is nothing but 1 minus summation of y minus y cap whole square by summation of y minus mean of y whole square. So what exactly is the question there? Y cap, this y cap you are going to get from the equation. This y is something that you are going to get from the question ka table. Okay. And this y cap you will calculate using the x values that are also in the table. Those x values you take, you keep here, you get a y cap column, another y cap column, and then you already have y. You put those values here in this r square. That's it. You will get your answers. Till in the class, we did all of this. Like, this is way too much. We were finding mean and then we were finding beta and everything. We get different y when we solve for given data. We get different y when we solve for given data for intercept and slope. Okay. So, okay, they are asking for R square value and once you are calculating it, are you getting the answer? Sometimes the model will give you rubbish answers. Okay. So even for that also you have to calculate your R values. In the previous one, they have used solved intercept, not for the given equation. Okay. See, I only know this method. Okay, this is the method that I will follow if I'm given such question in the exam. And this is what is the textbook definition of R square. Okay. So I will prefer this one, but I'm not sure what they have used in the last round. Then how did they solve it if they have not taken the equation one? Just give me a second. I'll look at the last year's one as well. I mean, last run as well. For the 10th time, yes, I will send, I will upload in week 7 and 8. Okay, I will upload as soon as this session is done. Explanations. They're only giving answers, no? They only gave answers, no? Okay. Okay, I'll ask about this one because this is the only way that we follow. Okay. Because in the formula itself that you are seeing that you have to differentiate in between the predicted value and the ground truth, right? So this is how we usually do it. Okay. I'll try to talk to them. We'll see that one. Okay. And curse of dimensionality and scaling in KNN. Uh, Okay, so when in KNN, whenever we are dealing with high dimensional data, no, so we kind of get some problems. Like in case the first thing is the computational cost increases a lot as the dimensionality increases. The computational cost of finding the nearest neighbor also increases significantly. This makes KNN impractical for larger data sets and also the one which has like way too many features. And also overfitting is also possible in higher dimensional spaces. So it can increase the risk of overfitting, where the model becomes too complex and fits the training data too closely to each other and leading to poor generalization of the new data. Okay. And scaling in KNN is scaling the features so it KNN relies heavily on the distance measures to find the neighbors, and features with different scales can have different impact on the distance calculations. Okay, so without the scaling, the features with larger magnitude can bring bias into the KNN algorithm towards those features. So which will lead to inaccurate predictions. So so we also do some standardization to it. We kind of do some min max scaling. Okay. And then we also remove the outliers and all of that. Okay. So yeah, that is pretty much it that you wanted. Okay. So okay guys, I'll stop here. We are 10 minutes over the slot. Okay. Thank you all for joining. Prepare well for your exams. Do really, really well. Okay. And also, all the best to all your other exams and all your things that you wanted to start or do or you're already doing. And you guys are like my first set of people that I'm teaching on NPTEL. So yeah, that's you have been like really amazing students to me because I keep talking with my fellow colleagues and compared to what they have faced, I'm really really happy that you guys are my students. Okay, so yeah, with that we are ending this problem solving sessions. And thank you guys. Thank you so much for joining and have an amazing life ahead. And in case if anyone is joining IISA anytime soon, please let me know. Just ping me. I will be available. Okay. Okay. Thank you so much. Thank you so much, everyone. Have a great day. And we'll stop here. Thank you.